Welcome to Modern Physics Lab number 2, where we're going to be predicting velocity and looking at the motion of a falling object. So first we're going to go over the fundamental physics concepts, talk about some major assumptions, really look at our results, talk about our axes and our origins, look at our computational model and how to construct it, and then we're going to compare that model with our experiment data, and then we're really going to talk about and explain the results. So again, we're using Newton's second law here, and this is kind of our fundamental principle. Now, what this law really says is that we're going to be predicting our terminal velocity using the fact that we know our net force divided by our mass, going to times that by delta t, or change in time, and going to add an initial velocity. And again, with that, we are predicting final velocity. Other important things to note here is that our net force is not going to be equal to zero, which basically means that we won't be dealing with a very simple and easy constant velocity. So some major physics assumptions is that we're working with two forces, our weight force and our drag force. Also, our initial velocity is going to be this zero vector, which basically means that our object is initially at rest. Also, the net force here is going to be equal to our force due to gravity, in addition to our drag force. So in our final models that we look at, we're going to show some comparisons with why this is important. So to kind of go over our results, our computational model actually under predicts our observed position, and our model that includes drag force is going to appear to be more accurate than the one without drag force. Now that's going to be very, very important, and we'll explain why later in the video. So again, looking at our axes, our origin, and our motion tracking software tracker, note that right here we have our origin point. We're going to be using a standard XY coordinate system with the negative Y direction is going to be pointed this way. It's the negative Y direction, and the positive Y direction pointed this way. So that's important because of the way we've oriented our axes, we're going to be moving with a negative velocity. Our object will have a negative velocity. If we went and we flip the axes, then you would notice that the negative y would be in this direction and positive y would be in this direction, and the graphs I'm about to show you would actually be flipped, if you will. So kind of going over to our computational model, you notice that we have to have some initial conditions when building the model. So big things to note are our g value is going to be equal to 9.8. This kind of arbitrary b value that we get from correlating the terminal velocity of our computational model with our observed data. It's a little bit arbitrary, but it'll make sense later when you see the graph. We also have this position vector j hat. And then another major thing to note is that our ball's initial velocity again is the zero vector. So our ball is initially at rest. Another thing that we're assuming is that for our final model that we're going to look at is that our net force is going to be a combination of weight force plus drag force. So here, similar to what we've used in prior videos, we're going to be using Newton's second law. This is the Python code for it, Newton's second law. And again, the big things to note here is that our net force is going to be composed of our weight force plus our drag force. And again, this drag force is going to be proportional to the square of our ball's velocity. So that's very important. It's proportional to the square of our ball's velocity. It's also going to be pointing in the opposite direction of our ball's velocity. That's why we have that negative there. And again, we use all of that to get to plug this into our position function, which is actually what we graph. So as a quick video, this is going to really show are two forces. Here you have the weight force, and here you have the drag force. So important thing to note is that our weight force, the magnitude of this arrow, is obviously constant, but we notice with the drag force, the magnitude of this arrow actually increases the longer time goes on, because drag force is increasing as our as our velocity is increasing. So over time, the drag force increases. Now here, this kind of has a graph of all of our different models, our experiments position, without drag, with drag, and then right here we have our this dark green line, our model that has drag and a non-zero initial velocity. Important things to note here is that if our initial velocity is non-zero, that the magnitude of our terminal velocity is actually going to be a much greater than when it's in any of the times when our initial velocity is zero. So a non-zero initial velocity gives a greater magnitude for our terminal velocity, which basically translates into a much a different slope here, of steeper slope, if you will. So kind of in conclusion, when you look at our drag versus our no drag graph, you notice that our drag model is definitely more accurate, but again, it's because of that B constant. Neither of the models really accurately predict terminal velocity because both models underpredict underpredicted. Our B value again comes from correlating our observed and our model's final velocity. If our object was thrown downward, then the terminal velocity would be greater and our drag force would be greater. And some potential errors that we may have had, notice that our axes may have been a little distorted because of the background of the picture, and there may have been some distortion in the center of mass. It was very hard to determine because it was paper. And that's my video.